So welcome back to the academic section. This is the first session for Room A today, and the overall topic is about the innovation and research related with orthopedic surgery. And in this session, we have 4 experts and they will talk with us about the innovation. So the first speaker, he is our past president of the Royal College of Orthopedic Surgeons of Thailand and also immediate past president of Mahidol University. And he will talk to us about finite element analysis for orthopedic research, past, present, and future. Let me introduce Professor Banchong Mahaisavariya. Professor, please.
Thank you, Mr. Chairman. And good morning, everyone. My topic will be just to inspire the next generation about what happened to my life concerning about the finite element study. Finite element study, I have heard about this term in 1985 during my second years working at the Kongkhet universities. This term has been mentioned by one of the staff from Faculty of Engineer, who is the consultant for high buildings, information about the list of failures and also stress and strain analysis using finite element study. He graduated from Berkeley University, but I don't know about how it will be useful in medical field until almost 2000, 1 year before 2000. I have been appointed as adjunct professor at the Asian Institute of Technology and being advisor for PhD student. And one of the PhD students come to ask me to be advisor for a project related to reverse engineering and finite element study for human body structures, which I'm very interesting, and I recall about the finite element in many years that I have heard about this term. Anyway, come to the definition of the finite element study. It has been mentioned and using the concept as a divide some complex structure into a small piece of element, definite number. And each of the elements will contain force, material properties, and also integrate together, have joined together in every node that will transfer from one node to another and from one element to another, and summation to give the whole structures for the information about the stress and strain that occur at the structures. And this technique has been used widely in engineering part, especially for big company like in application for aircraft structures and aerospace engineering. For the biomechanics in medicine, the name that has been recognized is the Donald Carter's in 1985 mentioned about using finite element study to determine about the stress and strain occur in proximal femurs, which really close to that of Wolff's law that we have learned. And this will be really powerful in biomechanics to recognize that finite element study can demonstrate something that we have never been measured before. For the information about the step in finite element in medical fields, this composed of 6 steps and 2 steps. First 2 steps is very important The first step is from medical imaging, CT scan or MRI, and convert into geometric reconstructions. And these two steps, maybe we call it reverse engineering. Reverse engineering. And this is a very important emerging technology before we can utilize the finite element study. At that time that I'm study about this in 1999. Although the CT scan can have some software to create three-dimensionally, but actually to create finite element study, we have to have another software to create some composition of material property in each of the pixels. And another software is to make a matching for the boundary of the whole structures. So this is emerging technology that bridge between medical imaging to create finite element study and pass through the reverse engineering technique. And after that, we can create the boundary condition and loading. And the result will show the stress and strains that occur in the object that we test using computer program software and create on the computers. And also we can have stain energy density, which is very important, and I will explain in the future. My PhD student from Asian Institute of Technologies study about using some program for reverse engineering. And this is the first paper from Thailand in determine proximal femur shape using reverse engineering. You see, this paper has been done completely, I think so, about 2001, and published in Medical Engineering and Physics in 2002. And this is the first paper using reverse engineering in proximal femur. I think so perhaps it's very early, and also this paper has been cited more than 250 citations already. And this also a key stone for using the image and also the software that create the reverse engineering to be the next step for the prototype, rapid prototyping. At that time we call rapid prototyping. And later on it called 3D printing. At this moment they call 3D printing. And my first paper also published in 2006 using prototyping, rapid prototyping for practicing. And also we have created some targeting device or something. And at this moment, no one, I think the new orthopedic surgeon don't know about the term rapid prototyping. They know only 3D printing. But actually at that time, we concentrate in certain aspect, but in big company, they progress using same technique, melting some of the power of the metal to create something and using as a very similar type of rapid prototyping to create new prosthesis or something, and so-called is very progressive at this moment. First publication for finite image study during 2003, we have published in conference paper, and I think it is very early in using finite image study in medicine globally, and including this paper is from Thailand, published in Injury, the first paper from Thai member of TOTS, 2006. You see, 20 years already that I'm take lead in finite image study in orthopedic surgeries. And this is, the question is, during that time we have several cases of gamma nailing for trochanteric fracture, and some people have problem with prominence of the proximal part of the nail. And we wonder that should we remove the nail or should we remain as is? From the study in our Thai cadaveric size, it's very risky to remove the gamma nail because it will create high risk of fracture necks in our Thai patients. So I advocate that if the patient have symptom of irritation, just take medicine to suit the problem. And the powerful of the finite element study is to create something that for the complex geometry in human bone and for the heterogeneous or anisotropic materials, especially for the bony structures. And we also have the problem with multi-axial and time-dependent loading, that this is very important to apply during the finite element study. And the outcome of this can be overcome by patient-specific geometries and spatials, varying material properties, and also physical loading application that we can create. We can also using finite element study for implant design optimization, including the plate and screw, and also the prosthesis, either short or long one, and either the shape of the stem to measure about the risk of straight laser effect or any loosening that will happen. And we can also design the plate thickness, the screw hole, and also design for any spatial site or location of the fragments of the bone to make it a good window for the implant system. And at this moment, we can customize by 3D printing for special or personalized implant system. This is another benefit. Material selection, either stainless steel, titanium, or cobalt, because all of these have difference of the modulus of elasticity that will create some problem with the stretch shielding. So we can optimize which one will be a good target to be developed. And also we can make use of the finite element study to evaluate the structure that perhaps better or suitable for secure the fragments and also minimize the problem of loosening or failure. We can also using finite element study to evaluate the bone implant interactions. This paper I will mention about most of the time that we using finite element study of the hip joint and also for the testing of the proximal femur, we will use the model of single leg stand or in upright position, stand on the effective extremity. But before this time, we understand that loosening or cut out of the bone usually occur mainly more than 50% occur within 2 months. With the patient do not walking with that position. So we make another model of testing by patient lying down using swing or lace up of the hip to measure about the torsion stability, which never before mentioned about this model. And this paper has been published in 2024. And I think this model will be popular in the future to measure the torsion stability of the implant, because if we test in upright position, the result is different. And most of the time you will receive message of patient stand on that hip and measure the stability of certain implant that you want to evaluate. But actually, most of the time, the implant failure occur before the patient stand. It occur at the early stage during non-weight bearing, bedless, sitting on the bed. So this paper is landmark paper. And another one is the strain energy density. Never before, they mentioned only Wong-Mai stress to evaluate the list of the breakage of the metals of the implant system. But the strain energy density is very important for loosening. That is the energy around the implant that will create loosening of the implant system. So this paper mentioned about the strain energy density. And in the future, it will be very important to mention about this. And for the percutaneous fixation of fracture necks, this paper, I myself, during my active life, I perform percutaneous screw fixation for the femoral neck in Thai patient in posterior triangle, because inverted triangle is very difficult in Thai patient because the bone is so small. You have very narrow space for two screws at the proximal part. So I mostly use a three triangular with posterior triangle, which very effective also. And we prove that it's also effective, very equal to inverted triangle. And this is another one. We wonder about the FNS, femoral neck system, whether it can create stability, especially torsion stability at the first early stage. And using the same model that I mentioned. And this has been accepted already by Journal of American Academy of Orthopedic Surgeons, which is, I think, two papers mentioned about this new model of testing. And I think that because they accept this paper, they also accept this model of testing. And I would say that this is the new model that proposed from Thai orthopedic surgeons, from this TOTS member. And other benefits from finite image study in orthopedic context is joint contact mechanics, cartilage degeneration and osteoarthritis, tendon, ligament, and enthesis biomechanics, and also in research in industry. For the futures, I think it will enroll in patient-specific finite image study in the futures. And also AI will enhance certain aspects. And real-time will come. Real-time and rapid finite image study will come. And we can also multi-scale orthopedics modeling in the futures. And I appreciate that new generation also interesting in finite image study. This is the paper from Professor Kongkhet, and more detail, Dr. Nattapon will be talking about this. And current paper from Surasak about the gap of the femoral metaphysis, how long it will be risky for failure. And also benefit of the non-vascular fibroid graft that will diminish the problem of the risk. And more detail, I think Nattapon also one of the researchers that will explain more. Finally, I would say that finite image study review invisible internal mechanics. Is explain failure, degeneration, and adaptation of the bone. Future finite image analysis will predict outcome, not just only stress or strain. And it will be very essential for modern orthopedic thinking, especially our field in orthopedic trauma. Thank you.
Okay, so thank you, Ajahn Banchong, very much about the insightful lecture. So the next lecture will be bringing clarity to orthopedic trauma engineering, which will be delivered by Professor Nattapon Chantarapanich. He is currently a Dean of Faculty of Engineering at Sriracha Kasetsart University. Please.
Right. Okay. Good morning, colleagues. My name is Nattapon. Once again, I am from Kasetsart University. And today I would like to present the topic of the bringing clarity to orthopedic trauma engineering. So of course, I'm not a surgeon, I'm an engineer, so I will talk more into the engineering aspect that relate to the clinical aspect. So I would like to explain a little bit about the essence of the orthopedic trauma, because I think everyone here know that, okay, we always have the complication cases or the cases that we are debating which treatment techniques or approach that we should apply for treat that specific patient. And then, so when we have the issue like this, we normally we try to debate which one is good or which one is not good based on the literature reviews. So why don't we try to apply the digital technologies, particularly for the finite element analysis, to help the surgeon to identify the proper way of managing the complicated cases. So normally when we have the orthopedic trauma issue or problem, we have to have the certain method to get the solution, to find a way or to draw the conclusion that we might have for that specific management. So the method here, when we test, we normally divide it into two methods. The first one is what we call the biomechanical test, which is sometimes we call as the direct method, and also another one we call it as a computer simulation. Sometimes we call it as numerical method. But if we deep down into the detail, direct method is more or less about the experimental test or biomechanical test, which you apply the actual loading into the bone model that you created according to the specific fracture cases or the cases that you want to find the solutions. And another one is a numerical method. It's the one that Professor Banchong just mentioned. Is about to use the tool, for example, the finite element analysis or other digital tool, for example, like 3D printing or also reverse engineering to help you and find a solution for you. But one thing is that normally based on the concept, the direct method always gives you like 100% accurate result, whereas the numerical method, for example, finite element analysis, it gives you the approximation solution. So you need to have the proper like assumption or definition assigned to the finite element model to get the reliable solution for the analysis. So if we talk about the biomechanical test, normally is like what I just mentioned, is about to create the model and to, for example, using the 3D printing model, the one that in the past time we call as the rapid prototyping. And then you create a model and you create the figures, and then you apply the actual loading into your model. However, the biomechanical test is not limited only the 3D printing based model, but it can be also applied to the cadaver model as well. But for the finite element analysis, is more or less, let's say, not the physical test, but is more in the computer test. So normally we work in a computer and we have 3 steps to achieve it. The first step is about the pre-processing, which is you need to define the geometry. For example, you apply the reverse engineering techniques to create a 3D model, and then you need to assign the proper material behavior model and do the matching, including define the contact condition between the bodies in the FE model, and also apply the proper boundary conditions. So actually, when we talk about finite element analysis, most of the time, not only surgeon but also engineer as well, sometimes most of people think that it's like a magic, but it's not like such that magic. But you need to have the proper assumptions to set into the FE model to get the reliable solutions. Once you set up the pre-processing finish, normally it's a computer task to do the analysis, and then you get the analysis results. So I would like to emphasize a little bit on the analysis result, because sometimes when we look like the contour band on the right hand side at the screen right now, it's like, oh, it's very sexy when you see the contour band. But underneath that is about how you interpret the result based on that contour band. This is very important. So I would like to talk about choosing the right tools, because sometimes we don't have to, let's say, apply finite element analysis in all cases that you want to analyze. It depends on many factors, but I would like to summarize into four factors. The first one is that if it's difficult to mimic the in vivo actual behavior, of course you probably need to apply the let's say finite element analysis to do it. The second one is that if it's difficulty to set up the in vitro experiment, of course finite element address that questions. And also if you have too many cases you want to try and also included in the study, of course finite element is a solution. And if you don't have like enough budget or it's limited with the expense, so finite element is also the answer for you as well. So what the FE can do, actually we can apply to analysis in many cases, as Professor Banchong already talked about. For example, if you want to clarify, let's say, the conclusion of the treatment strategy, you can, for example, try everything in computer. For example, in this case, you have the you think about using the non-vascular fibular graft combined with the locking screw fixation for the metaphysis bone loss for the distal femur, and then we think about how to manage. Should we have the screw or should not screw apply? So normally we just try to create a 3D model with a different scenario. For example, using the lateral distal femoral plate alone, or you have the medial column plate as well, or you change medial column plate into the non-vascular like graft, or you just put the non-vascular like graft plus with the additional screw for that. So normally when we do like this, we have to look on not only the contour band on the right hand side, which is of course showing the stress high or low, but you have to check on also the displacement that occur in the model as well. And on the middle pictures that you are seeing now is the displacement of the construct for the whole construct. So you probably see that if you look on the third pictures, 1, 2, 3, the third case, the graph actually moved from the middle size into the lateral size. So in this case also, we apply the finite element to seek for the conclusions for the treatment strategy, which is we have 3 different plates or fixation techniques for the clavicle fractures. So normally we apply the FE to seek for the optimal solution, and then we apply the clinical case based on the solution of the finite element analysis. And apart from the treatment strategy, we can also study about the optimal fixation strategy as well. For example, in this case, we have a debate about which the screw configuration should we apply for the distal femoral fracture gap, and we have also the wide range of the femoral fracture gap, right, from 0 to 80 millimeters. So when we combine all cases together, we have a 9 case. Of course, you cannot do it experimentally. You need something to help you reduce the work. So we try to have a full DOE, which is stand for the design of experiment, combining everything. So we have allow not 9 but actually 27 cases in total. So which means we need to do simulation for 27 cases. This is impossible for the experimental analysis. So in this case, we have the very big data to analyze which configuration or which fracture gap should be addressed by the different techniques. Also, this one, we also use the finite element analysis to do the optimal fixation strategy for the different level of the subcontracted fractures. So in this case, we vary the fracture level A, B, and C, and also we also apply the different strategy for for the screw fixation as well. So actually for this case, we have 54 cases in total. Of course, it's impossible to do the experimental test or even the cadaveric test. So this is the key that the finite element helps you to do the research or to do the work to get the solution for you. And apart from the optimal fixation technique, you can also either study about the selection of the appropriate fixation. For example, in this case, it's not about for the finite element, but it's more or less about the biomechanical test. What we did, we created all this model by the 3D printing techniques. Why we have to do 3D printing? Why don't we use the cadaver? Because cadaver, we have a different property across individual to individual. So it's quite uncertain to use the cadaver to do the testing like that. And of course, we don't have enough cadaver to apply for all cases that we did. So the point is that we control everything the same, shape, properties, and also the material that built the let's say the 3D printing model to do the biomechanical test. And in this case, we apply the different technique for fixation, like the double tension wiring, or like the crossing one. And then we also apply the different test method like the posterior bending, medial bending, lateral bending, and also torsion as well. And at the end, we also have a nice graph for analysis, like which one should be applied to manage the distal humerus fractures. And also, we also able to apply these technologies for for example, like the ramus fracture case as well. Actually, when we do the experimental like this, the thing that difficult for us is the fixture design, because when you try to do like it, it's not only the printing and then you just put the loading on, but you need to know how to design the proper fixtures to get or to mimic the actual situation in your body as well. And also this one is the same. It's just the same application that Professor Banchong has already said. And I would like to highlight the key is that finite element help you to visualize something that you cannot see in real life. For example, if you want to see deformation, it's quite difficult to detect what happened in the patient or something like that. Particularly, for example, like the SED, which stands for the strain energy density, is the energy that the material absorbs. So you cannot detect this in the patient, but you can visualize it in the finite element analysis. So if you look on the medullary nail on the right hand side pictures, you see like the big band of the white color over there is indicate that this is the high SED area, which is potentially can causing the screw loosening. And also just the same as the future of FE. So it's going to be more like individual FE for the customized fixation design, just the same in this case. In this case, it's like they have like the bone with the cancer, and then we try to design the particular fixations for treat this specific patient. So what we do is that we do what we call the quick finite element analysis, which is we do the quick 3D model and then quick implant design, and then we do everything in the computer to do the analysis, and then we confirm the strength, and after that we just send the 3D model of the plate to do the customized machining. So this is also the case that's going to be the future in real soon. So of course, this work here cannot be done with only me alone, but also the cooperation of the surgeon and also engineer. So I would like to promote the collaboration between these two disciplines. I think that would be building the great work in the trauma engineering in the futures. So thank you very much.
Thank you very much, Professor Nattapon, for a very impressive talk. So the next one will be moved to 3D printing. in orthopedic surgery. And the next speaker is our president of our of Royal College of Orthopedics, Surgeon of Thailand, Professor Keerati Charoencholvanich, under the topic of in-house 3D printing in orthopedic surgery. Professor, please.
Dear Chairman and Co-Chairman, and dear our colleague and ladies and gentlemen, I would like to share experience about in-house 3D printing point of care operative in orthopedic surgery. Anyway, before I give our topic, I would like to invite all of you to join our great year of Royal College Orthopedic Surgeon of Thailand. I would like to speak in Thai in this version before giving the talk of the topic. ปีนี้นะครับเราจะครบ30 ปีการสถาปนาราชวิทยาลัยแพทย์ออร์โธปิดิกแห่งประเทศไทยและ60 ปีราชวิทยาลัยแพทย์ออร์โธปิดิกแห่งประเทศไทยครับเราเกิดวันที่18 พฤษภาคมนะครับตั้งแต่เป็นชมรมออร์โธปิดิกไทยนะครับการเวลาผ่านพ้นมาจนถึงวันนี้ก็ครบ30 ปีการสถาปนาจากราชวิทยาลัยคือ Royal Establishment ในวันที่18 พฤษภาคมและเราจะครบรอบจากชมรมในวันที่11 ตุลาคมพอดีนะครับก็จะครบ60 ปีนะครับขอเชิญชวนพวกเราทุกท่านนะครับเข้าร่วมภาคภูมิในงานเฉลิมฉลองวันที่17 พฤษภาคมที่ห้องนภาลัยโรงแรมดุสิตธานีนะครับก็จะบรรจุเชิญพวกเราได้ประมาณ460 ท่านนะครับก็อยากให้พวกเราได้ร่วมภาคภูมิกันตั้งแต่ครูอาจารย์พี่น้องตั้งแต่เจเนเรชันต้นๆเลยนะครับจนถึงเจเนเรชันใหม่ๆของเรานะครับมาร์คปฏิทินไว้นะครับ17 พฤษภาคมนะครับตั้งแต่5 โมงครึ่งตอนเย็นนะครับอีกหนึ่งงานก็คือวันที่18ในเช้าวันที่18จะมีงานของ ARCOS 60 Diamond Jubilee from Heritage to Horizon เราจะกราบครูระลึกถึงข้อคุณครูที่ราชวิทยาลัยแพทย์ออร์โธปิดิกแห่งประเทศไทยแล้วนะครับอาคารเฉลิมพระบารมี50 ปีที่ซอยศูนย์วิจัยนะครับตั้งแต่9 โมงเช้าจนถึงเที่ยงนะครับก็เรียนเชิญพวกเราทุกคนนะครับเรามีวันนี้ได้เพราะมีครูมีพี่สร้างมาร่วมกันระลึกถึงและก็จะให้ครูได้ทราบว่าอนาคตได้ฝากฝังว่าอนาคตของราชวิทยาลัยไทยเราจะเดินหน้าไปทางไหนไปกันอย่างไรนะครับวันที่18 พฤษภาคมด้วยนะครับระหว่างการเฉลิมฉลองของ60 ปีนี้นะครับราชวิทยาลัยเราได้จัดโครงการเพื่อประชาชนหนึ่งในนั้นก็คือเรื่องของหมอออโถชวนเกล้าหมอออโถประดิษฐ์จะมอบสุขภาพให้ประชาชนในการเฉลิมฉลองของเราโดยเชิญชวนประชาชนทั้งประเทศร่วมกันเดินออกกำลังกายดูแลสุขภาพและเพื่อ13 โรงพยาบาลในครั้งนี้เราจะขอRaising Fund ในการที่เราจะไปให้กับพี่น้องออร์โธปิดิกไทยที่ทำหน้าที่อย่างเข้มแข็งที่ขาดแคลนอุปกรณ์ทางออร์โธปิดิกนะครับ13 โรงพยาบาลมีอะไรบ้างสูงเม่นแพร่บัวน่านโกสุมพิสัยมหาสารคามจตุรัสชัยภูมิยุพราชเลิงนกทายะโสธรโพนพิสัยหนองคายหล่มสักเพชรบูรณ์ทองผาภูมิกาญจนบุรีชะอำเพชรบุรีบางสะพานประจวบคีรีขันธ์หลังสวนชุมพรไล่ลงมาถึงใต้ท่าโรงช้างสุราษฎร์ธานีและใต้สุดนะครับสมเด็จพระยุพราชสายบุรีปัตตานีจริงๆแล้วส่งมาถึง50 กว่าโรงพยาบาลนะครับแต่เรารับไว้13 โรงพยาบาลก่อนเพราะ13 โรงพยาบาลนี้เราต้อง Raising Fund ถึง100 ล้านบาทนะครับตอนนี้เราร่วม Raising Fund มาได้80แล้วนะครับยังขาย20นะครับคาดว่าเราจะน่าจะได้ถึงเป้าเมื่อวันที่3 พฤษภาคมแล้วก็จะเชิญชวนประชาชนไทยร่วมกันบริจาคจนถึงกลางเดือนนี้ในการเฉลิมฉลองของพวกเรานะครับหนึ่งในการ Raising Fund ก็คือการร่วมให้ทางภูมิภาคจัดงานเชิญชวนชาวไทยร่วมออกกำลังกายนะครับเช้าวันนี้หมออโถชวนเกล้าจัดที่พิษณุโลกประชาชน 3,000 กว่าคนก็เข้าร่วมโครงการนี้นะครับก็เกิดความสำเร็จยิ่งใหญ่ในการที่จะเชิญชวนประชาชนดูแลสุขภาพนี่คือที่พิษณุโลกเมื่อเช้าวันนี้เองนะครับก็ขอบคุณกรรมการทุกท่านสมาชิกทุกท่านและเชิญชวนให้ร่วมกันเชิญชวนประชาชนอีกนะครับเรายังมีเวลาเชิญชวนประชาชนโดยใช้ออกกำลังกายโดย Virtual Run 1 บาท1 กิโลเมตรที่ท่านประชาชนร่วมวิ่งจะมีผู้บริจาค1 บาทให้กับ13 โรงพยาบาลนะครับเช้านี้พิษณุโลกเราได้จัดมาแล้วก่อนหน้านั้นก็คือที่นี่คือเมื่อเช้านี้เองนะครับท่านผู้ว่าราชการจังหวัดก็ให้เกียรติในการนำประชาชนชาวพิษณุโลกแข็งแรงร่วมพลังกันนะครับแล้วก็จังหวัดก่อนหน้านี้ก็คือราชบุรีมากมายเลยนะครับ ประชาชน 2,000 กว่าคนก็เข้าร่วมในโครงการนี้บริจาคเงิน500 บาทได้ลดภาษี2เท่าและเงินเหล่านี้ก็จะเข้าไปสู่13โรงพยาบาลของพี่น้องออร์โทปิดิกไทยนะครับอุบลราชธานีก็จัดไปแล้วนะครับก็ทำให้ประมาณ 2,000 กว่าคนเช่นกันนะครับแต่ละที่ก็ทำให้เกิดความร่วมมือของภาคของราชวิทยาลัยกับทางชุมชนของแต่ละที่เชียงใหม่จัดที่แรกเลยนะครับเมื่อเดือนที่แล้วนี่ก็โอ้โหได้รับความร่วมมืออย่างมากมายจากเดิมที่เราจัดแค่500 คนก็เพิ่มเป็นเกือบ 3,000 คนนะครับแล้วก็ที่นครราชสีมาเพิ่งจัดไปแล้วรวมทั้งถึงเรื่องของบางสะพานประจวบคีรีขันธ์และอุดรธานีที่ได้จัดไปแล้วก็ยังเหลืออีก4-5 ที่เลยนะครับคือสุพรรณบุรีหาดใหญ่เชียงรายแล้วก็ชลบุรีที่จะจัดและนครศรีธรรมราชอีก5แห่งนะครับหากพวกเราพี่น้องเราร่วมพลังกันในภูมิภาคได้ก็จัดนะครับเพื่อนำเงินเหล่านี้ไปช่วยกับหมอออโถน้องๆเราพี่น้องเราเนี่ยครับที่ปฏิบัติงานอยู่ตรงนั้นนะครับ so the next topic that I would like to share is the in-house 3D printing in the orthopedic surgery. This will be outlined for 4 sessions. The first one, introduction and background. And second one, Sirat factory in the box. The first factory in the box 3D printing in the world. And concept, what is it? And the third one is clinical experience. And the last one is Sirat experience and future perspective. For the concept, the paradigm shift from because of the traditional of the shelf implant right now is more and more requirement of complex trauma case and often require the improvisation of the implant and require personalized more and more implant for the patient. The solution is transitional from outsourced industry manufacture to point of care 3D printing in-house. So why we need 3D titanium printing? Because right now more and more complex case occur and require patient-specific solution and enhance precision and reduce complication of surgery and point of care manufacturing. And we need biocompatible implant and complex case management can manage much more in the hand of surgeon more easier and safe. And the first factory in the box point of care at hospital is we create at the Sirat faculty that manufacture of 3D printing titanium hip and socket in the proven clinical successful. For the begin at the national level collaboration exhibit to set up the new company. We call it osteo. Os it means bone. Tree is tree. Organization collaboration is the osteo. And MOU signed at the 24th of June 2 years ago. And joint venture between the faculty of Sirat Medicine, Sirat Hospital, Mahidol University, and medically private company and supported by Program Management Unit for Competitiveness, PMUC. That is, and we set up this factory in the box at the Golden Jubilee Medical Center. Sirat Hospital Global Breakthrough is the world's first compact modular point of care manufacture system. And we located at the Golden Jubilee Medical Institute. And the key feature is modular titanium implant production, shipping containment format in the very small containment, and AI automation, VR integration, and enhanced speed, precise and personalized that solve the problem of requirement. We see in this graph that we are in the first one on the right side that can successful factory in the box, point of care. That means factory that in the center of service. Usually, maybe they have a 3D printing factory, but out of the service center that take time and take requirement of shipping or time for requirement. But right now, we can success in the point of care center. That is the only container, shipping container. You can see The model on the left side is only one container can produce in the body, approved that 3D printing titanium to use in the human. That our successful for this one because we need to require approve from the FDA. System feature is a clean room, very important that very clean. Is finishes is already made and ready to use out of the factory in the next room. Going to the operative theater, you can use that. And the medical grade metal polymer 3D printing and producing control pan with the software that we need to work together between surgeon and engineer. System feature is a surgeon collaboration platform with the VR and AI assist, implant design, and integrate hospital IT and quality control. Real implant success. We first implant in the factory in the box, how point of care in the Sirat faculty. We successful. This patient require personalized implant on the 12th of March of last year. That's almost 1 year already. And we declare our successful by the press conference on the 2nd April of last year. It's the first time of point of care factory in the box 3D printing. And that time our deputy, the minister, come to join and declare our success. Press conference on the 2nd April. That means we ready to use and spread our success. Thailand Vision, which is a medical hub, we would like to be one of the success and collaborative with another institute and another country. We need to be, we want and we aim to be the global leadership. Sirat Hospital global benchmark in the precision medicine. In the medicine, they have precision medicine. Surgery, orthopedic, we have a precision surgery with the 3D printing titanium, printing for the individual patient. And Thailand medical technology leadership in this region or Asia Pacific and patient center innovation commitment. So that we need collaboration, synergies between many organizations. We want to share our experience. The first one is 72 years Thai male, and with 30 years ago have a pelvic fracture and right hip osteoarthritic, bilateral secondary hip arthritis, and perform knee total hip replacement at 2008. Anyway, 3 years ago it's septic loosening, and this patient have required take the implant out. That the 2-time surgery. And 2011 the surgeon do trabecular metal cup cage system. But later on, on a second year, 2 years later on, polyliner shell already exchanged because redislocation, and 2023 is infected again. This patient, anyway, at the last one is the right side that no major massive bone loss, particularly on the acetabulum side. This case, we decide to use the 3D printing. That means we take the CT scan and discuss with the engineer which real time, which side, which position, and which bone defect that we need to replace with the 3D printing, and which the keyhole screw, home run screw, which one we use to place the screw to fixation between the titanium printing and the host bone. As this one, the center, you can see that the direction of screw we can manage and we can plan, even though it's only 5 millimeter thickness. That the direction is very important to catch up the screw to secure the implant to the host bone. That we can do that in the 3D dimension. And after we discuss with the the whole that like a like one we can design as a hook design to the crest of the host bone that this have a big major bone loss, but in the host bone that enough we can plan any direction, any position, and we have a plastic template before implant the real one to set up the simulate situation. And this is the real 3D titanium printing. We opened from the box of the factory that finished and using with this patient. That X-ray finding this the reduced operative time and safe for the surgery. That we make our tough case to be handled under handle case. This is the X-ray after surgery. And another case at the Sigirat faculty right now we use this one aseptic loosening on the right side. You can see this very strength of configuration of the implant that because is this is one the modular implant that we use two pieces to be fit in the host enough. This another design. And in aseptic loosening of the left hip, we can see that we can design at a cone shape big one to fit in the host bone that well fixed enough and primary stability create after surgery. At the right side again, the same as this one is another example case that we can use titanium printing and individualized to replace the major bone defect. And this one may even though is osteoarthritis due to bone loss from infection, we can create. We don't have to use the modular one again. We use the 3D titanium printing to see it on the individual host bone. For the post-trauma, this one is again that major trauma we have. Maybe some cases we need to use a 3D printing like this one to replace the host bone that the big defect of the fracture. And another one is complex periprosthetic fracture that we can use this create of individualized position of this one. And this is another case of case that we use for acetabulum part. Another case that we like this one fracture, that late fracture and the thread of the pin, thread of the screw penetrate and destroy the host bone, and we can use only one piece of titanium to replace the host bone. Another situation like this is another case of aseptic loosening, and this case for the bone tumor, the big bone defect. This one is the right pelvic chondrosarcoma. We have to resect the big bone and replace with the big titanium printing of this one. And this the left side, the tumor specialist already take it out, and we decide to replace the same time of the printing. And even sarcoma in some finger, we replace with the metaphysis all of this one. Then success without any use, because in the past we have to use allograft and it's collapsed later on. And this time we use a titanium. So in the future perspective, in the technology, we need to expand is a multi-specialty application, particularly trauma. I think we need that more. And AI automate design. We put the CT and then it's automate the design for us. And smart implant monitoring. And regional vision, we need to be a Asian 3D printing hub and factory in the box network. And also the patient and community will have a cost reduction. So thank you for your attention. Thank you.
Okay ครับ Thank you อาจารย์เยติครับ for your lectures. So the last lecture would be from Dr. Navapong Anantavorasakul from Lersin Hospital. He's a specialized in wrist, hand, and upper extremity trauma. He will deliver the lecture about in-house 3D printing center breakthrough the limits. So we may have to rush a little bit.
Hello. ขอพรีเซนเตอร์โน้ตด้วยนะ Okay, good morning, Chairman, Co-Chairman, and dear participant. My name is Navapong from Lersin Hospital. Today is my honor to be here, and I would like to introduce you to our 3D printing center in Lersin Hospital. And as we know that our 3D printing has become more popular right now, especially in the orthopedic surgery, and nowadays we increasing managing the difficult fracture and deformity, and particularly in some region that anatomy is quite complex, like the pelvic and the sternum. And despite the advanced imaging study, the conventional 2D CT scan still require us to mentally reconstruct the complex anatomy, and this can be challenging and may lead to the interoperative uncertainty. So sometimes we have to spend time and on the trial and error and play contouring and repeated implant adjustment, and also longer exposure of the radiographic of the radiation and addition. And in addition, some standard implants are designed for the average anatomy and may not perfectly match with the individual patient. So for this reason, we consider the custom 3D printing as a practical solution. The patient-specific anatomy model allows us to visualize and better understanding complex fracture pattern or deformity before the surgery. With the model, we can simulate the osteotomy and reduction the perioperative time and improve the planning and reduce the interoperative uncertainty. Implant can be pre-contoured using the model, which can significantly reduce the timing. Finally, in selected case, customized implant may improve the anatomical fit compared with the conventional implant. In our experience, 3D printing is not used routinely, but we can use the technology as a problem-solving tool for the complex case. And today, I would like to share our experience in our 3D center. This is a short video. We have the 3D printing center in our department. Our center has been open since November 2024, so we have run this center about 1 year approximately, and 3D center is located in our department. We have the vision to be the leading 3D printing center, and we can provide a solution for managing the complex patient, advancing the medical education and research in every level from the medical student to the fellowship training, and also the support the medical innovation to maximize the benefit for the patient and Thailand healthcare system. In summary, our 3D center have three main aspects, including the medical service for taking care of patients, improve the medical education, and support the innovation. In our center, we have three main printers. The first one is the 450 MC, which used to print the thermoplastic, such as the ASA or PCISO, which is the biocompatible material. The next one is a J850 digital anatomy, which can print with the resin using the polyjet technology. With this printer, we can mix up the material to achieve a single model with a different property in the same place. For the model can be used to replicate the anatomy of the patient and can use in many purposes. And the last one is a one-click metal machine, which use the selective laser melting technology to print the titanium alloy, which is also the medical implant grade, so we can print the implant for the patient. We can use the printer to make the customized implant for the specific patient or any prototype for the medical instrument. And this is the floor plan for our center. In our center, we have the engineer that are available in the center for helping the doctor to do the segmentation and design the implant together with the doctor. So this cross communication is the key of success that can shorten the time of our workflow. In general, we can finish the process within a few days. So next, I will move to some of our experience. The first is for the service for taking care of the patient. First case is a 53 male with a deformed right wrist for 5 years. You can see that he has a very malunited distal radius. With the CT evaluation, there is a severe malalignment, and the distal part of the distal radius is very small, so it cannot be fixed with the conventional plate that are available in the market. So we use the software to segmentation the bone, and we use the contralateral side of the wrist to be the mirror image and use it as a reference. We use a 3-point reference technique to align the articular surface together. And then we identify the proper cutting plane and realign the model together. After that, we also design the cutting guide and reduction guide for this patient, using the same KY position to make sure that the reduction guide can put into the right position. And we also design the customized plate to fit with the distal fragment for this patient. And with this is a video that we take while we print out the titanium plate. And we can achieve the plate like this. There may be a weird looking plate because the fragment is quite deformed. And we also print the model for the simulation to practice the surgery before we go into the real case. And this is the implant. We can take this one into the OR too. And this is intraoperatively. We have the model and we have the cutting guide, stabilize with the KY, perform the cutting. The alignment can be correct, but unfortunately in this case we have the problem about the length because the prolonged shortening of the forearm. So we have to combine with the ulnar shortening osteotomy. And anyway, we achieve the very good alignment of the bone. And you can see that the alignment of the wrist is become normal. And this is the post-operative film. Next example case from Dr. Pongsakorn is a male, 30 years old with a neglected femoral neck fracture. We analyze the fracture pattern using the information from the CT. And there is a neck sharp angle about 100 degrees and retroward of the femoral head. So first, we simulate the reduction. We try to test that after traction, what position can be achieved in the software. So we get the better fracture approximation. And then we design the surgical guide for the cannulated chisel to perform the fixation, and also the walk-out osteotomy guide to perform the walk-out osteotomy. And intraoperatively, we traction and make sure that we achieve the traction at the same level as we plan. We use the guide for the chisel, and also guide for the osteotomy, and we perform the bone cut. And this is our intraoperative film. So we can achieve the good reduction and precise precision of the chisel to the proximal fragment. Next case is a 79 male patient with a delayed comminuted fracture of the middle phalanx of the little finger. So you can see that the proximal phalanx drives into the middle phalanx, and from the CT scan we erase that we cannot reconstruct this bone. So maybe we consider the fusion for this case, but in this case we discuss with the patient and we decide to create the middle phalanx prosthesis. We use a mirror image from the another side to create the prosthesis, and we design the hole for the collateral ligament reattachment, the central slip reattachment, and also the different surface of the bone, the articular part that have to be polished, and other part that have to be rough surface to integrate with the tendon. And this is the implant. Intraoperatively, we use the dorsal approach with the preserve the extensor apparatus and remove the fragment out, insert the implant in, and apply the suture to reattach the all collateral ligament and central slip. And we also decide to implant to have the center hole for the temporary fixation with the KY, and we plan to remove it at 4 weeks. And this is a post-operative film. We just did this operation about 3 weeks ago, so we don't have the result right now. Another example is the case for the non-displaced scaphoid fracture. Normally, we can do percutaneous fixation using the fluoroscope, but we know that this operation may rely on the experience of the surgeon. So with the CT scan, we can identify the axis of the scaphoid for the percutaneous screw fixation, and then we just design the hand mold for the patient. So we make the hand mold that are perfectly fit with the skin of the patient, and then we print out. We use this intraoperatively. So we have the patient hand in the same position with the CT scan. So we know which is the axis of scaphoid. We can do the percutaneous fixation with a single attempt. And when we put the guide wire into the correct position, we just proceed with the other procedure, like putting the headless screw fixation. This is just an example that we use the 3D technology for the patient. For the education, the patient-specific model can give us a very good detail for the deformity evaluation. We use the model for the pre-op planning and surgical simulation. And also for the workshop, we can print out some saw bone that have the specific property that is better than the normal saw bone. Like in this case, we print out the hand model for the KY workshop. We have the soft tissue component, then print by the resin, the polymer, to simulate the skin outside of the bone, to simulate the percutaneous KY fixation. And also, intramedullary canal can be replicated by the hole inside, so we can do the intramedullary KY, and we test it under fluoroscope too. For the last aspect of our goal of our 3D center is for the innovation. So every orthopedic surgeon have a lot of innovation in your mind, but the problem is we cannot convert the innovation into the real product. So this 3D printing center can help you to solve this problem. This is an example of the customized internal joint stabilizer. Maybe some of you will know the implant we call IJS from the Skeleton Dynamic company, but it's not available in Thailand. So we use the same concept and design some implant. This is a neglected complex elbow injury. So we design the pin, the axis pin for the distal humerus, and connect that pin with the plate that's placed on the ulna. And to achieve the correct axis of the distal humerus, we also design the guide for the axis pin. And this is the simulation that we plan to achieve. So it's like we convert the external fixator, the hinge external fixator, into the internal fixator. But the patient can continue moving the elbow without the implant outside. Another innovation is the arm positioner for the elbow surgery. Normally, when we do the lateral decubitus, we have to put the arm on the arm positioner. This is my colleague. Thank you for being my model. The problem is the arm plate for the arm positioner is usually with the metal plate. So the problem is if we want to make the intraoperative fluoroscope in this area, the metal plate will block the bone and you cannot erase the fracture. Like if you want to do the meatball technique for the humeral shaft fracture. So I designed the relucent arm positioner using the relucent material and use it in the same manner, like this. Can support the big arm of my colleague. This is an example of the case. You can see that on the very proximal part of the humerus, we can see with the intraoperative fluoroscope very clearly. So for the current situation right now, in last year, our center have finished about 77 projects, and we have print out more than 300 models. Most of the projects are for the service case. It means that we use it for treating the patient. And some of the projects are for the medical education and other for the new innovation. In the future plan, we have really willing to collaborate with other hospitals. So all of you guys, if you want to achieve this technology, please visit our small booth in the walkway. You can take the brochure. In there will be the QR code, so you can contact us through the line of your account and just send us a CT, and we can discuss with our engineer to decide what you want, and we can help you. And we try to find a way to reimburse this kind of 3D product, like the 3D model, 3D cutting guide, or even customized 3D printing implant, to reimburse it with the universal coverage of Thailand, and also try to get more patent of our innovation. And also, if possible, we can convert our innovation into the market. Okay, and thank you for your attention. And before the last slide, I would like to introduce our first workshop for the orthopedic surgeon. And we will have, in this year, we will have the deformity correction using the 3D technology workshop. It will be held on the 26th May 2026. So please keep in touch. You can add in the line of your account, and we will have more detail announced later. And next year, see you in Kongkhet. Thank you very much.
So thank you very much for all of the speakers. So we have no time for Q&A. We will move to the next session. And thank you for all of participants for your attention. Thank you.